Hello everyone, welcome back to my YouTube channel Unfog with Dr. Atahar Parveen. In this class I am going to discuss Electronics and Communication chapter based on HSTR syllabus. As we are going to expect the notification soon, it's better that we start from a tough chapter which is Electronics and Communication, and this class will be the first part of this chapter. If you have not subscribed to my channel, please do like, share and subscribe to my channel, and please explore this channel as well, because you will find many classes based on physics and mathematics for HSTR aspirants. Okay, not only HSTR aspirants, even all the teacher recruitment examination aspirants can follow my channel, because I make classes based on maths and science for GPSTR and TET and HSTR as well. Okay, so please don't forget to like, share and subscribe. Now let's start the class.
And in this class I will cover so much portion. I will finish till PN junction diode. I will talk about conductors, insulators, semiconductors, their meaning and examples, energy bands and solids, and then bias types, doping, dopants, PN junction diode, then Zener diode. Actually they have not given in order. If they have given in order, no, then this syllabus first Zener diode should have come, then this LED, photodiode, solar cell, and then transistor should come, because they are all interrelated, right? Without discussing the basic we cannot go for higher explanation, right? So I am following the order which I am comfortable with. And many of you were asking for syllabus of HSTR and CRIS. I have posted the syllabus in Telegram channel. You can join the channel if you are new to this YouTube channel. You can join the Telegram channel and you can check out there. You have this syllabus. Now let us start with this chapter, electronics. Electronic means solid, right? It deals with solid materials. So what is a solid material? That solid material, it could be conductor, it could be insulator, or it could be a semiconductor. So solids, they are classified into three types: conductors, insulators and semiconductors. Now what are conductors? These are the materials, or these are the substances that allow electricity to flow through them. How does electricity flow through them? They have free electrons on their surface. When they have free electrons on their surface, then these electrons will allow current to pass through them. So current will flow smoothly in conductors, or electricity transmits freely through conductors. For example, our human body. Our human body is also a conductor. Why? We get shock, right? When we touch any open circuit, when any uninsulated wire is fallen down, we touch it, what happens? Current flows through our body, right? Many people die also with that. That is happening because current can easily flow through our body. Next are insulators. What are these insulators? They are the substances which don't allow current to pass through them, or they resist current. Why they resist current? Why do insulators resist current? Because there are no free electrons in them. No free electrons means no current flow. No current flow means they are insulators. Okay. Example, best example is glass. In fact, this glass, it is the strongest insulator. Why? Because it is giving more resistance. It is having high resistivity. It does not at all allow current to flow through it. Okay. So these are insulators. Now there are one more materials which are very important and with which electronics deals. Electronics basically deals with semiconductors. We all are going to study only about semiconductors in this chapter, electronics. Okay. So what are semiconductors? Semiconductors means they are neither conductors, they are neither insulators. They are somewhere in between conductors and insulators. These semiconductors, they possess moderate or low conductivity. Why is it so? Because in semiconductors, there are no free electrons at 0 Kelvin temperature. Why we are telling about 0 Kelvin here means if you increase the temperature in semiconductors, free electrons occur. Those electrons which are not free at 0 Kelvin, they move. Some of the electrons, they start moving. Means some free electrons may occur in semiconductors when you increase the temperature. That means semiconductors can conduct at high temperature. Okay. These materials are known as semiconductors. Now, if I want to talk about resistivity of these three, conductors, insulators and semiconductors, by now you must have got idea, right? What about conductors? First of all, what is resistivity? It is the property of a material that tells about how that material, it opposes or it resists the flow of current through that material, isn't it? Now, what is conductivity? Conductivity means something which is opposite to resistivity. Conductivity means it is a property of a material by virtue of which it allows current to pass through it. Okay. So resistivity is opposite of conductivity. So what about the resistivity of conductors then? Resistivity must be very low, isn't it? Resistivity is very low. That's why conductivity will be very high. That's why it is a conductor, right? Then what about insulators? Here resistivity will be very high. That's why it's not allowing current to flow through it, right? That's why conductivity will become low in insulators. What about semiconductors? Semiconductors means they are intermediate. We don't know, it may be having moderate resistivity or you can say they have moderate conductivity. Okay, whatever you choose, you can describe semiconductors on the basis of resistivity or conductivity. Usually we describe on basis of conductivity, right? Because conductivity is a good habit, right? Conducting means it is allowing current to pass through it, right? So that thing you can keep in your mind. Now, these are the examples of conductors, semiconductors and insulators. See, as I told you, for conductors, conductivity will be high and electrical resistivity will be low. For insulators, conductivity will be low, electrical resistivity will be high. And for semiconductors, it will be in between the conductors and insulators. Now, what are the example of conductors? Gold, silver, water, copper wire, and our human body. These are the best examples of conductors. Then insulators, anything you pick up, it is your wish. Glass, as I told you, it is the strongest insulator. Anything, a paper bird, plants, bottle, bag, your abacus slate, your toy or glass, as I told you, all these are insulators. In semiconductors, if you want to see the naturally occurring elements from the periodic table, then silicon and germanium, they are semiconductors. Okay. And many, like there are many things like artificial things are also created nowadays. Whatever you see, the electronic items, the ICs, the integrated circuits, the diodes, the LEDs, all these come under semiconductors category. All this we are going to learn in this chapter. Now in this chapter, we are going to talk all about semiconductors. Now, inside a solid, each electron, it will have a unique position, right? So each electron, it has a different energy level. These energy levels, they are so closely packed that we call them as energy bands. So you can say that energy band means group of energy levels. What are energy levels? Energy levels are those where electrons are situated, right? Now, there are two types of electrons, we know it. They are valence electrons and the second is the conduction electrons. Now, what are valence electrons? Valence electrons are those electrons which are in the outermost shell of an atom. Then what are conduction electrons? Conduction electrons are those free electrons which conduct electricity, isn't it? Now, there is one band which contains valence electrons. That band is known as valence band. And the band which contains conduction electrons is known as conduction band. Now, if you want to show them in a graph, how you show is, you put a energy level here. Because we are talking about energy levels, right? So, here below there will be valence band. Okay. And conduction band, it will be above. This is a conduction band. So what you say? Conduction band is a high energy band and valence band is a low energy band. So energy is high right here in conduction band. So conduction band is a high energy band and valence band is a low energy band. Usually in conduction band, there are no electrons, right? Why there are no electrons? Because we are talking about free electrons. Conduction electrons are free electrons, right? They are freely moving to conduct electricity. So usually conduction band, it is either empty or it is partially filled by nature. Okay. But it is never fully filled. Conduction band, it is never fully filled. So this you can keep in mind. And in valence band, valence electrons are always present only. Whatever the condition in valence band, valence electrons will be present. Now, there is a distance between these conduction bands and valence band, right? There is some distance. Now, depending on this distance, this conductor, insulator and semiconductors are described. Now, the distance between this conduction band and valence band is known as energy gap, or they also call it as forbidden energy gap. Why forbidden energy gap? Means there are no electrons right here. There are no electrons and it will not allow electrons to go through it also. Because it is not any band. It is just a gap between two bands. Now depending on this, we describe conductors, insulators and semiconductors. In conductors, this conduction band and valence band, they are overlapped. So electrons in valence band, they can move freely to conduction band. Because there is no distance. Actually here, this entire thing, they are overlapped. Here conduction band is also there, valence band is also there. This is not the gap between conduction band and valence band. In conductors, this conduction band and valence band, they get overlapped. That's why electrons from valence band, they can easily go to conduction band. Now that energy gap which we told, no, the forbidden energy gap, the symbol for that is Eg. Here what happens in conductors, Eg will be 0, right? Because conduction band and valence band, they are overlapped. See, whatever points I am telling, you either note down. It's better you note down. Any point can be asked as a MCQ in HSTR or CRIS. Okay? So please listen carefully. I know that you all know this already because you must have studied all this in BSc. You must have studied all this in 12th. But what happens is because of time span and because of our other responsibilities and other works, sometimes we forget what we have read. So you can think that my classes are sort of a revision class. Okay. I assume that you all already know this. But only thing is that maybe few of you must have forgotten the concepts or few of you might have not read these concepts at that time properly. You never know, right? Okay. So coming back, this was all about conductors. Now this graph, no, wherein we draw this conduction band and valence band, it is known as energy level diagram. Now what happens in insulators? In insulators, there is a large gap between conduction band and valence band. So you have this Eg, you will have some value here in insulators. What will be that value? This is energy, right? So the unit should be EV. The value will be more than 3 EV or 3 electron volt in insulators. That's why they are insulators, right? Now electrons, see. Here the electrons, they traveled from valence band to conduction band. But can they go? They can't go here in insulators from valence band to conduction band, right? Because there are no electrons here. It will not even allow this forbidden energy gap. It will not even allow electrons to move from valence band to conduction band. This is not possible here. That's why they are insulators. They cannot conduct electricity. Now there are one more materials. They are known as semiconductors, which are very important for us now. In semiconductors, there is an energy gap, but it is not as much as insulators. That means conduction band and valence band, they are not very far. They are nearby. How much nearby? This Eg, forbidden energy gap, it will be less than 3 electron volt. Or if I want to say precisely, in semiconductors, the forbidden energy gap will be nearly 1 electron volt. Okay. So these are all 1 mark questions. They can ask you as MCQs. Now because the conduction band and valence band is nearby in semiconductors, So we can say that the resistance in semiconductors is not as high as insulators. So at room temperature, valence band will be partially filled and conduction band will be partially filled. Few electrons they can go. Not many, but few electrons they can go. When they can go? Only when you increase the temperature. This is not possible at 0 Kelvin. It is not possible at 0 Kelvin. When you increase the temperature, few electrons, they will get energy, they will gain energy and they will move from valence band to conduction band. Now, best examples for semiconductors are germanium and silicon, right? Usually what they do, they ask the value of this energy band gap in this semiconductors. For silicon, it will be 0.7 eV. You have to remember the values. For germanium, it will be 0.7 eV and for silicon, it will be around 1.1 eV. So you have to remember these values. These are very common questions. They have been asked in the MCQs. See, don't take HSTR and very lightly. I have analyzed your question papers. I feel that they are very high level questions actually. They may be questions from KAS or KPSC level. Okay. So you don't take it lightly. You should know all the important points from whatever topic you have read. Okay. Now, as I told you earlier also, electronics is all about semiconductor materials. So from now onwards, we will talk about only semiconductors materials. Now let us have a look at this table. This is a very, very important table because any point can be asked as a 1 mark question from this table. This table, it will describe everything about conductor, semiconductor and insulator. It talks about forbidden energy gap, how it is behaving. Then conductivity, resistivity, flow of current, temperature, coefficient of resistance. Then what are the charge carriers in conduction band, charge carriers in valence band, examples and applications. Okay. So all these are important points here. Before looking at the table, I want to talk about one very important point from this table only. That is temperature coefficient of resistance. This is a very common question asked in any competitive exam. So temperature coefficient of resistance for insulator, it is negative. And for semiconductor, it is negative. But for conductor, it is positive. Why? See, when I say the temperature coefficient of resistance is negative for insulator and semiconductor, I mean to say that with increase in temperature, resistance is decreasing. As temperature increases, resistivity decreases for semiconductor and insulator. Why is this happening? Because what is happening is when electrons will gain energy. Why electrons are gaining energy? See, when you increase the temperature, then electrons will gain energy, right? The energy is increased in that semiconductor or insulator. When you increase the temperature, the electrons will gain energy and they will move freely to conduct. That's why increase in temperature means you are increasing the conductivity. Increasing the conductivity means you are decreasing the resistivity, or the resistance of that material decreases. That's why we say that temperature coefficient of resistance, it is negative. Negative means, see, temperature is increased, resistivity is decreased, isn't it? There is a negative impact of temperature, right, on the resistivity. That's why we say temperature coefficient of resistance is negative. This is happening both in semiconductors and insulators. But what happens in conductors? We say that it is positive, right? Temperature coefficient of resistance is positive in conductors. Why we say like that? Because when you increase the temperature, no, electrons are already freely moving. They gain more and more energy with increase in temperature. Now, they were doing their job, they were moving. Now you are giving more energy, what they will do? They will fight with each other. They will collide with each other. Now, because these electrons which are freely moving, they start colliding, then the flow of current will get disturbed. The smoothness of the flow of current will get disturbed and their resistivity will be increased. Current is disturbed means resistivity is increased, right? So increase in temperature is having a positive impact on the resistivity. That's why we say that conductors have positive coefficient of resistance. Okay, so this point, in fact, I am expecting this time, because till now they have not asked this question, but this is a very, very important question. So I'm expecting this question this time, either in HSTR or CRIS. Okay, that's why I have specially mentioned this point. Now let's have a look at this table. See, as I told you, in conductor there is no forbidden energy gap. In semiconductor it is very small when compared to insulators. It is around 1 eV. And in insulator, that conduction band and the valence band, they are very far away. That means forbidden energy gap, it is more, that is greater than 3 eV. Then you have to remember these values also for conductivity. It is a conductor, means the conductivity will be high, right? So the unit for conductivity, it is opposite of resistivity. So for conductivity, it is opposite, right? So conductivity will have mho per meter. These are the values. It is high for conductor and it is low for insulator. And for semiconductor, it is medium. Okay. They will not ask these values, I feel, but still you just have one idea about these values. About flow of current, due to movement of free electrons only current flows in conductor. In semiconductors, due to movement of electrons and holes, that we will talk. We have not talked about semiconductors, right? So this point we will talk about this. Next, charge carriers. No, in conduction band, in conductor, conduction band is completely filled. Why? Because conduction band and valence band, it is overlapped, right? That's why conduction band will be completely filled. But in semiconductor, it will be partially filled, because only few electrons can jump from valence band to conduction band. In insulator, it is far away, somewhere in desert it is fallen, you can think. So in that conduction band, no electron can go from valence band. That's why it is completely empty. And in valence band, it is almost vacant in conductor, because no, from valence band almost all electrons, they go to conduction band and they conduct electricity, isn't it? Then in semiconductor, it is partially filled, and in insulator, it is completely filled. Now examples for conductor: copper, aluminium, graphite, etc. And semiconductor, best examples are silicon, germanium and arsenic. Then insulator, I have told you already. Then applications. Applications are very important, especially for semiconductors. The applications are diodes, transistors, optocouplers, and many more applications are there, which we will talk in this chapter. Okay. Now this is a question which was asked in GPSTR. It is a previous year question paper from GPSTR, but it's a very important question. It is that at absolute zero temperature, room temperature, and at very high temperature, the germanium crystal, it acts respectively as whatever the option is. You just remember this point. At absolute zero temperature, a crystal or a solid of pure germanium, that is a semiconductor, it behaves as a perfect insulator. I told you, right? If you increase the temperature, then only the conductivity will increase. At absolute zero, it is a typical insulator. So option C will be the right answer. Next expected question. This is an expected question. Which is the best conductor? See, actually the best conductor is silver. Then you will ask, madam, why in our wires, in our housing circuits, there is no silver? Because it is costlier, guys. You know it, right? Silver means chandi. It is very costly. How can people afford putting it in housing circuits? That's why we use copper. Okay, so best conductor is silver. Then one more question. This question is from HSTR. Your previous year question paper from HSTR. Okay. The energy gap between valence band and conduction band in a silicon semiconductor is silicon. Either they give silicon or no. They are giving this word semiconductor, right? And they are talking about semiconductors, means your energy gap should be less than 3 electron volt. If they are giving you equal to, then it will be equal to around 1 electron volt. Okay. Now when we are talking about insulators, semiconductors and conductors, it's better we talk little bit at least about superconductors. Superconductors are those materials which have zero resistance at very, very low temperature. For example, mercury. Less than 4.2 Kelvin. At less than 4.2 Kelvin. 4.2 Kelvin is already very less temperature, right? Below that temperature, if you keep that mercury below that temperature, then it will conduct vastly. It will become a superconductor with zero resistance. Okay. So this is known as a superconductor. Now one question was asked here. A material that has zero resistance is called. It should be a superconductor. One more question could be superconductors. They have almost zero resistivity. Isn't it? That's why they are superconductors. Resistivity is opposite of conductivity. You remember that. Now, which one of the following is the most conductive element? Same thing. The most conductive element is silver, I told you, right? Same thing. Maybe they will give you in a twisted manner. You should remember the most conductive element is silver, but we use copper here in housing circuits. Copper is also a good conductor, but it is best is silver. Okay. Next question. These are all expected questions. A pure germanium crystal at absolute zero is. Pure germanium crystal means it is a semiconductor. They are talking about semiconductor. So, a semiconductor at absolute zero, it will be a insulator. Okay. Next question. Current carrier in conductors is, obviously they are electrons. Which group among the following is insulator? You see the groups. So the best group I find is paper, glass and cotton. Okay, this is the insulator group. Next question. The band gap between valence band and conduction band is the measure of. See, usually we measure with conductivity, the conductivity of the material. The more the band gap between the valence band and conduction band, the worse is the conductivity of the material. What is the inverse of resistance called? The inverse of resistance is called conductance. The energy gap is maximum in, of course, in insulators. It is maximum in insulators. There is no energy gap in conductors and a very less energy gap in semiconductors. Now, in a conductor, charge carriers, they are only electrons. We know it, right? But in semiconductor, charge can be carried not only by electrons but also by certain particles known as holes. We cannot say them as particles actually. Actually, what are holes means, usually electrons, they are charge carriers or they are responsible for flow of current, but in their absence from particular place in an atom, some vacancy is created in that atom, isn't it? So that vacancy is called hole. Now we say that electron can be passed from one atom to another, right? So we can also say that hole can be created anywhere from where that electron is getting absent. That's why we say that hole can also be passed similarly like electron. Because whenever electron is making some place, that is a hole, right? So if electron is moving, it means that it is creating that vacancies from wherever it is getting absent, it is creating some holes. So we can say that holes also can pass. Now, for example, see if there are two electrons which are moving from valence band to conduction band, then this is the place from where the electrons are absent now, isn't it? The electrons, they got absent, isn't it? Because they have moved to conduction band. So now those vacancies, they become holes. Okay, like that you remember. So holes, they will be in valence band, then electrons, because they went to conduction band, here holes, they are created in valence band. Now these semiconductors, no, they can be divided into two types of semiconductors. First is intrinsic semiconductor. The second is the extrinsic semiconductor. In intrinsic semiconductor, number of electrons is denoted by N suffix E. Number of electrons is always equal to number of holes, N suffix H. That means how many electrons they have passed from one band to another. So many holes are created in intrinsic semiconductors. Now this is also equal to Ni. Ni means density of electrons and holes. Okay. In intrinsic, Ne will be equal to Nh. This will be Ni. This is number of electrons and holes present there. Now at room temperature, electrical conductivity, it will be very low in intrinsic semiconductor. So we cannot use this intrinsic semiconductor in our electronic devices. Because at room temperature, conductivity is very low, right? It cannot work as it should actually work. So what we do? We need to improve their conductivity. Now this can be done by adding some other substances called impurities in these intrinsic semiconductors. When a few parts per million means ppm. when few parts per million of suitable impurities added to pure semiconductor, then what happens? The conductivity of that semiconductor, it will increase many times. Now after adding that impurity, that intrinsic semiconductor, whatever we achieve it after adding that impurity, that is known as extrinsic semiconductor. Okay, and the process of adding this impurity in intrinsic semiconductor, it is called doping. And those impurities which you are added, no, they are called dopants. Okay, you can say that doping means adding impurity to intrinsic semiconductors. Now the result of these are extrinsic semiconductors. Dopants means those impurities which are being added, okay, to make them extrinsic semiconductors. Now for this also few rules are there. Simply you cannot take something and add it. It's not like this. Usually these dopants, no, they are pentavalent, means they have valency 5, or they are trivalent, means they have valency 3. Example for pentavalent, what they are, here I have written it, right? For pentavalent it is phosphorus, arsenic, antimony, etc. And for trivalent it is gallium, boron, indium and aluminium. So this you keep in mind, because they are asking all this, anything can be asked in your question as a MCQ. Okay. Now we are talking about extrinsic semiconductors, right? These extrinsic semiconductors, they are two types, N-type and P-type. When you say N-type means it is negative type, you can say. When you say P-type means it is positive type, you can say. Okay. Now what happens in N-type? In N-type, the majority charge carriers. Now we have two types of charge carriers now in semiconductors. You got it, right? They are electrons and holes. In conductors, they were only electrons. But here in semiconductors, they are electrons and holes. In N-type, what happens is your majority charge carriers will be electrons. That's why we say them that they are negative type, right? We say that they are N-type. Negative, here majority charge carriers are electrons, means what will be minority charge carriers? Minority charge carriers will be holes. Okay. Then in P-type, what will be majority charge carriers? They will be holes. And minority charge carriers will be electrons. These are all 1 mark questions. You have to remember this. But see, having said this, as a whole, crystal, it will never be positively or negatively charged. Crystal is always neutral. Okay. We are talking about the flow of electrons in N-type and P-type semiconductors. But as a whole, crystal will be neutral. So in N-type, majority charge carriers are electrons. They are negatively charged electrons, and minority charge carriers are positively charged holes. In P-type, majority charge carriers are holes and minority charge carriers are electrons. Now I can also say that in N-type, number of electrons will be very much more than number of holes, isn't it? Because majority charge carriers are electrons. And in P-type, number of holes are more than number of electrons. This you have to remember. Now we told that the impurities are pentavalent and trivalent, right? Now these pentavalent or plus 5 valency elements, they are used as dopants only in N-type. Okay, in N-type semiconductors, pentavalent dopants are used, and in P-type semiconductors, trivalent dopants are used. If you just remember these elements, no, they are enough. They are very commonly known elements which are used as dopants. So questions also will be based on these elements only. Now, when we are talking about this doping and dopants, no, we are playing with the covalent bonds. We are adding the pentavalent or trivalent dopants and doping the N-type and P-type semiconductors such that the covalent bonds are completed, so that they become a good semiconductors, means they conduct electricity. Okay. Now, usually the donor impurities, no, they contribute for free electrons, and acceptor impurities, no, they create hole. Okay, this you have to remember. Donor impurity means whatever electrons are given, no, from the impurity, they are donor impurities. If there is a hole means then they are acceptor impurities. Now this was all about p-type and n-type semiconductors. Now let us see few MCQs based on this. Pick a statement that is correct for a p-type semiconductor. In a p-type semiconductor, if I see the options, the majority of charge carriers in a p-type semiconductor, it will be holes. This is the right option. Then n-type semiconductor is, see what I have told you, right? It is not negatively charged. It is not negatively charged. We say that here majority of charge carriers are negatively charged electrons. Okay, but the particular semiconductor, the material itself, it is not negatively charged. It is neutral. I am expecting this question this time. Okay. Next, which of the following impurity added to silicon will give a p-type semiconductor? What I told you, for a p-type semiconductor, you use trivalent. Trivalent means aluminium. It should be the right answer. Now, this question was asked in HSTR. Similar question. The dopant which is to be added to a pure semiconductor to get p-type semiconductor, it should be aluminium. Now, I am giving you one detailed table to remember this. See, in n-type semiconductor, you can make it by doping 14th group element with a 15th group element. In p-type semiconductor, you can produce the p-type semiconductor by doping 14th group element with a 13th group element. Actually, 13th group element means it will have 3 valency, trivalent it is. Okay. Now, 15th group element means it is pentavalent. Just remember n-type with pentavalent, p-type with trivalent. So this is the table with which you can remember these elements. Now when a p-type crystal, it is brought into close contact with one another n-type crystal, then that resulting arrangement, it is called p-n junction or p-n junction diode. Actually, when p-type and n-type, they are separately used, they have no use. They have limited use, you can say. But when these two, they are combined, the p-type and n-type semiconductors, they are combined to form one junction. Many new characteristics will appear, which will make this particular setup one useful device. That device is known as p-n junction diode. Okay. If you put that p-type and n-type together, there is one layer between p junction and n junction. That layer is known as depletion layer, or that region is known as depletion region. One of the main use of this p-n junction diode, it is rectification. Rectification is not there in your syllabus, but you need to know because this is very important application of this diode. Rectification means it converts alternating current to DC current. So this can be a 1 mark question. See, this layer I was talking about. This is your depletion layer. Now we know that in n region, concentration of free electrons is higher when compared to holes, and in p region, concentration of holes is more than electrons. Therefore, when p-n junction is formed, some electrons from n region, they will diffuse into p region, and there they will fill the holes in p region. That means again covalent bonding, it will get completed here. Now this process wherein these electrons are diffusing from n region to p region, this is called as hole recombination. Here you have acceptor ions in p region. Okay, these are the acceptor ions. And there are holes. Holes are already present, right? Now electrons, they are coming in the p region and holes, they are accepting them. Same thing is happening in n region also. Electrons are already present there. Now holes, they are coming and then they are becoming this donor ions. And the between junction is known as depletion junction, and around that junction, that layer which we call the depletion layer is there, or you also called it as depletion region. Here what is happening? No current is there here. Now electrons are moving from N region to P region, and holes are moving from P region to N region. So there is flow of charge carriers, so there will be flow of current. But in depletion layer, that is not happening. There no some electrons and holes, they get bounded, they get trapped there. Therefore there is no current there. So you can say that the depletion layer, it is an insulator. Now what is the size of this depletion layer? It is around 1 micron. 1 micron means how much it will be? It will be equal to 10 raised to minus 6 meters. So much small it will be. Now this is the symbol of a PN junction diode. You have one triangle with a line, then there is a anode and it is a cathode is there. Now this PN junction diode with anode and a cathode, consider that if it is connected to an external voltage, what will happen? Some biasing happens here. It depends on your connection. So now in a circuit, no, if you put it like this, which is already there here, if you put it like this, then it is a forward bias. If you connect it in opposite direction, then it will become a reverse bias direction. Okay. Now assume that this is put in a circuit. If it is put in a circuit, then the P type, the P region should be connected to positive. The anode should be connected to positive terminal. Then it is a forward bias PN junction diode. If that P type is connected to negative of the terminal of the battery, if that anode is connected to negative terminal of the battery, then it will be a reverse bias. Okay, this you have to remember. Now also remember that in forward bias, the width of the depletion layer, it is very less. But in reverse bias, the width of the depletion layer is more. Okay, the depletion layer, it is of more width here in reverse bias condition. Now actually something is happening here when you connect the PN junction diode in forward bias, and something else is happening when you connect that PN junction diode in reverse bias. What is happening, I will tell you. First let us talk about forward bias. In forward bias, see what is happening here. Holes from P type, they are moving to N type, right? And electrons from N type are moving to P type region, right? Now what is happening here? The depletion layer, it is very thin here in forward bias. This is happening because more and more current is flowing. More current will be flowing in the PN junction diode. So it will force the depletion layer to be decreased, because less number of electrons and holes will get trapped here because there is more current. But in reverse bias, what will happen? No, there is very less current. Less current means there is no one to force the depletion layer to put out the electrons and holes. That's why this depletion layer, it will be of more width in reverse bias. Okay, for now you remember so much. Now there is a graph which we call as IV characteristic. We plot current on y-axis and voltage on x-axis, and we draw a graph for this PN junction diode. There are the two conditions are also included in this graph. First is the forward bias region also we plot in the same graph, and then reverse bias region also we plot in the same graph, and we compare to know in which biasing condition the diode is better. Okay. See, before I will tell you, in forward bias condition, the diode is better. In fact, it will conduct in a forward bias condition only. In reverse bias condition, it will not conduct. Now, I will explain you this graph, IV characteristic of PN junction diode. Actually, in forward bias condition, the current first it will increase. Non-linearly, it will increase up to some certain forward bias voltage. This voltage is known as a cut-in voltage, threshold voltage, or knee voltage. Okay. Then current will rise abruptly even if you not change the voltage. After this threshold or knee voltage, then current will abruptly increase even though you will not increase the more voltage. This is happening in forward bias condition. See here in forward bias condition, in volts I have written. In x-axis it is 0.2, 0.4, 0.6, 0.8. It is in volts. And in y-axis current is in milliamperes. It is 20, 40, 60, 80, 100. It is in milliamperes. Now coming to reverse bias, when you connect the that PN junction diode in the opposite manner, what will happen? Here current will be reversed because it is you are connected in reverse bias, right? So usually this current is known as saturation current. Why it is known as saturation current? because no, it does not change with change in voltage. See here in reverse bias condition, the current is in microamperes. See here in forward bias, current is in milliamperes, that means 10 raised to minus 3 amperes. But in reverse bias, it is in microamperes, that is 10 raised to minus 6 amperes. It is very much less, right? Here, that's why the current is very less. So you call it as saturation current because it will not change. Though if you increase the voltage, that current is not going to change unless and until you increase the temperature. For every 10 degrees centigrade of temperature, that current, you know what, that current is known as saturation current or I naught. That current, it will become double with 10 degrees centigrade. Okay, every time. So if you increase this voltage more and more in reverse bias, for particular voltage, large number of electrons and holes are produced. At this particular voltage, when large number of electrons and holes are produced, that region is called as Zener breakdown region. Now if PN junction, it is lightly doped, and in reverse bias, no, depletion region, it is more, right? It is large. Sometimes if you increase more and more temperature, some covalent bonds, they will break in this depletion region, and more electron and holes, these pairs, they are produced, and this also contribute to electric field. So at that time, your graph will become like this. So this region, at that time, it will be known as avalanche breakdown. So this was all about PN junction diode. Now let's see the expected questions. For a PN junction diode, the current in reverse bias may be. See, in reverse bias, I told you, right? In reverse bias, the current is in microamperes. Whereas in forward bias, the current is in milliamperes. So option D will be the right answer. Next question. A PN junction is said to be forward biased when? When you say that PN junction is forward biased, when positive terminal of the battery, it is connected to P side and negative terminal of the battery is connected to N side. So option A will be the right answer. Next question. A PN junction has a low resistance in forward as well as reverse direction, high resistance in forward as well as reverse direction. It conducts in forward direction only, it conducts in reverse direction only. A PN junction diode, it will conduct in forward bias only. Next question. A PN junction failure below 5 volts is caused primarily by, below 5 volts means it should be Zener breakdown. Then again more than 5 volts means it will be avalanche breakdown. Okay. If the positive terminal of the battery is connected to the anode of the diode, then it is known as anode positive terminal. It should be forward biased. Depletion region behaves as, I told you, right? It is insulator. The minimum forward biased voltage required for a diode to conduct is called, it is called threshold voltage. Then the threshold voltage of silicon and germanium, or the threshold voltage of silicon and germanium, it will be 0.7 volts and 3 volts. You have to remember these values. Now this is a HSTR question. What is a typical conduction voltage for silicon diode? It should be 0.7 volts. Next question. The device used to convert alternating current into different current is, actually it is a rectifier. That rectifier, it is made up of a diode. This is one of the very important application of a diode. Now let's talk about Zener diode. Zener diode means it is also one semiconductor, but it is heavily doped. Usually PN junction diode, it operates in forward bias region, right? We told it right now. But the Zener diode, it operates in reverse bias condition or in breakdown region. This is the symbol for the diode. For PN junction diode, we had one line just, right? Instead of that line in front of triangle, we put some line like a Z. This is the symbol for Zener diode. Its main application is that it is used as a voltage regulator. And this is the IV characteristic of a Zener diode. By seeing the graph only, we can say that the voltage, no, it is not changing much here. In x-axis, you can see for the reverse bias condition, the voltage is not changing much. Now this diode, it is fabricated by heavily doped P side and lightly doped N side materials. Now this will help in operating the reverse bias. It is same as PN junction diode as I told you, but the difference is that PN junction diode, it works in forward bias, but Zener diode, it works in reverse bias. So one question was asked like this: the voltage across the Zener diode it is constant in reverse direction. The voltage across Zener diode is constant in the reverse direction means it is behaving, the Zener diode, it is behaving as a ideal voltage source. Okay, that's why they use it as a voltage regulator. Now this is also one HSTR previous year question. A 6.2 volt Zener is rated as 1 watt. The maximum safe current the Zener can carry is, these are the options. Actually this has nothing to do with Zener diode, this answer, because we know that in current electricity we have read it that the power is equal to voltage into current of that material, whatever it is. It can be a Zener diode, it can be PN junction diode, it can be any other diode. Here they are talking about voltage because it is a voltage regulator, no, that's why. But then you have to use that formula only, power is equal to V into I. Substitute the values and you get the answer here. Okay, the maximum current will be equal to 161 milliamperes. Here option 1 will be the right answer. Now these are the questions which I am giving you as homework. You have to comment the answers for these 3 questions in the comment section. Okay, you can pause the video, read the questions and give me the answers in the comment section. Okay, then this was your first lecture on electronics. Please do like, share and subscribe to my channel. Also join the Telegram channel. Maybe whenever you need something, you have some doubts, then you can ask there. Okay, then thank you.